In classical mechanics, inertial mass is the constant of proportionality between the net force and the resultant acceleration. Mass determines how much kinetic energy is associated with a given motion because mass measures inertia, and inertia determines how much work is needed to create that motion. Inertia determines how rapidly a restoring force can change the motion, and that sets the natural frequency. A spring is an elastic mechanical element that stores potential energy when deformation force is applied. It releases this energy as the deformation force is removed. When a system is disturbed, a spring determines how fast a system naturally oscillates. Stiffness is the measure of a system's resistance to deformation, and its value changes from one spring to another depending on design parameters and material used. The higher the stiffness, the higher is the natural frequency and the more a system will oscillate. A damper is a mechanical element that resists motion proportionally to velocity, dissipating mechanical energy typically into heat and reducing oscillation amplitude over time. Damping ratio is a dimensionless parameter that measures how much damping is present in a system relative to the critical damping required to prevent oscillations. A system is said to be undamped if it had a damping ratio equal to 0 and it will oscillate indefinitely. This can be seen in ideal mass spring model for theoretical approximations. Can also be seen in LC electrical circuits with lossless approximation. Underdamped system has a damping ratio less than 1 and its oscillation will decay over time. Applications for underdamped systems include car suspension system, pendulum in air, where air acts as a passive damper. A system is said to be critically damped if it had a damping ratio equal to 1. This can be seen in aircraft control surface actuator or an analog moving coil meter. A system is said to be overdamped and its oscillation will decay to 0 really quickly. This can be seen in applications such as hydraulic door closer with slow return or heavy instrument pointer in viscous fluid. By using Newton's second law of motion, we will realize the resultant force from energy stored and dissipated is in the opposite direction from the applied one. By solving the differential equation and assuming a damping ratio less than 1, we will end up in an exponential decay sinusoidal solution. Damped frequency is the reduced oscillation frequency of an underdamped system due to damping. Spring mass damper system is foundational to control systems. By analogizing a complex system and reducing it to simple harmonic oscillation, we can get an insight about the system's behavior and how far away it is from our desired behavior. By adjusting the natural frequency, we can make a system respond faster or slower depending on the application.